Welcome, life science learners, to another installment of scientific methodology. In this lesson, we're going to look at how we present data, how we analyze the data, and how we draw conclusions. So if you recollect, over the past few lessons, we've looked at scientific methodology in terms of writing out an experiment, identifying variables. We then spent some time looking at how we present data and how we use graphs to illustrate trends of the data. In today's lesson, we're going to be looking at the analysis of data and how that helps us to draw conclusions. And so let's look at some important vocab. As we start off, we're going to look at some concepts of how to analyze data, how to analyze graphs, and how we link that to writing a conclusion. So let's get into the lesson, and let's have an overview of that lesson first. So have you ever thought about how does a scientist draw conclusions? So often you wonder about, you've conducted an experiment, you've got the data. What does that data tell you? How do you look at that data and draw a conclusion that links to the aim? And often we have the data, but it's difficult for us to interpret. And so we present that information in a graph. And so the graph makes that much more easier as an illustration to see trends of data. So by using a graph, we're able to look at that information, and we're able to see patterns of information, or patterns or trends in that information. And we hopefully are then able to use that information to link it to our aim. And remember that the aim is an investigative question. And that aim has to be answered using the data. And generally, we link our conclusions to the information that we have in the table or in your graphs, and we then link that to, have we answered the aim of the investigation? Let's look at that process today. So the challenge question is for you, relating to this section on scientific methodology, reads as follows. Which of these contains the steps of scientific method in the correct order? So I've got 4 statements here that give you a series of processes or steps. Let's identify these as a challenge question, which we could then clearly look at how we've looked at methodology and relate that to these questions. So A suggests, ask a question, do background research, state your hypothesis, conduct an experiment, analyze data, and make a conclusion. So that's one possibility. The second suggestion is state your hypothesis, ask a question, do background research, conduct an experiment, analyze the data, and then draw conclusions. Okay? Option C is ask a question, state your hypothesis, do background research, conduct an experiment, make a conclusion, and analyze data. And option D is state your hypothesis, ask a question, do background research, make a conclusion, conduct an experiment, and then analyze the data. Guys, these seem quite confusing because there's a whole lot of processes and steps that need to be followed. Let's move on to the next slide, and I'm sure that the information in the next slide is going to answer the options that are the most correct in this. So let's pay careful attention to what the next slide has. So going back to the concept diagram around scientific methodology, the first thing is we've got to ask a question. We've got to do some background research, and as mentioned, you've got to go and read about other research. So reading, going and finding information around similar topics. Then that will help you to construct a hypothesis, and then we link that to testing the experiment, which would be where we identify the aim of the experiment, and that is where we design an experiment to test a specific aim. You have a process of method that you need to follow, and that would either give you results in a positive manner, which is yes, or might not give you results. We then know that if you've got some results that are able to be collected, that we analyze those results, and then we draw conclusion. So this is where we are at today. Today we're looking at how do we use the data to draw conclusions. And let's look at the steps going forward. So when you have the data and you're drawing conclusions, there's 2 possibilities that might happen. You need to then analyze the results and align them to the hypothesis, and if they do, then you communicate your results. Or if not, if the results do not align to your initial hypothesis where you've made an educated prediction or guess, then you've got to review that, and you've got to go back to the experimental data, ask a new question, form a new hypothesis, and probably conduct an investigation to test your new hypothesis. And then when that succeeds, you then communicate your findings or your results. So this is an overview of the scientific method. Again, as I mentioned, that what we've discussed in this slide would be beneficial to you answering the challenge question. So again, an overview would be the first thing: observe and question. Research, read a lot about what you are investigating. Remember that scientists share information, and there's a lot of information that you can get out there related to your topic. This helps you to be more focused in your approach, in your angle to that. Formulate a hypothesis. Remember that it's a prediction, it's an educated guess or prediction about what you think might happen. Remember to link that to your variables, especially your independent and the dependent variables, which are fundamental to your investigation. Test your hypothesis using a scientific method where you design an experiment and you conduct that. That experiment allows you to collect data, which you then analyze and conclude. And so this is where we are today. We're looking at the analysis and conclusion, as well as writing your reports and then sharing those results. Okay, let's move on. So some key words in today's lesson. So we've been exposed to the word aim as a question of intent. The method is actually the experimental recipe that you're going to follow to conduct a series of steps to actually measure out or to measure out the independent variables' effect on other factors, which we know are the dependent variables. So we've been exposed to the terms dependent, independent, and control variables. Today we're going to introduce the terms analysis, inference, and conclusion in our lesson. We also know that there are terms such as correlation, which is essentially trying to see the relationship between one variable and the other. So is there a relationship between two variables? And the next term is causation, a new term that you might be exposed to, but we often refer to relationships on a graph, and we say, well, the one relationship is because of the other. So as the temperature increases, the rate of the enzyme activity increases. So we see that there's a correlationship between the two. However, there's a cause and effect, which we need to understand. So why does the enzyme activity increase? It's because the temperature is causing that effect. So that's a causation factor. So you need to understand the difference between the correlationship between variables. So as boys age, their height increases. There is a correlationship between the age of the boys and the height of the boys. But that's not a causation. That's not the cause of their height increasing. However, and in another example, we know that as the temperature increases, the enzyme activity increases. That's because the temperature provides the energy. So that's the cause factor. So that's the term causation. Okay? We've been exposed to the term valid, reliable, and accurate, which we need to incorporate into our analysis of results. A term that I'm introducing today is biased or subjective. Okay? So let's refer to the interpretation of color in a qualitative experiment. So if you're conducting an experiment where you're testing the presence of protein, and you know that when conducting an investigation, we often use a reagent that produces a color. So the interpretation of color can be very subjective. That essentially means that the way a person sees a color and the way a person sees another person sees that color can be slightly different. So often when you ask a friend, what do you think about, the appearance of my shirt or the color of my clothes, and they'll tell you, well, I think it's too light or too dark. And another person might think, well, it's okay, it's fine. And that's the subjectivity that we see. And this comes in when the data that you collect is qualitative, it's not quantitative. Quantitative is measurements. So qualitative data can be subjective. We also need to remember the word bias refers to a slight inclination towards a certain understanding or certain view of something. So, for example, if you are playing a soccer match with a team from another school, and if your teachers or coach were refereeing that, one could say, well, if a decision goes towards your school in that favor, that there's a bias because your teacher from your school is refereeing that game. So there's a claim of bias. And so the best way to be able to look at something that's unbiased is to have someone that is neutral that referees that game. So often in science, we need to look at information that is unbiased or that is not seen as being portrayed towards a specific angle. So we will refer to whether the information is biased or subjective. We also know that there are terms called interpolation and extrapolation. And that's got to do how we use information in the graph to find out how we could predict or extend the data in that table or in that graph. So let's get into some of the concepts in today's lesson. So I've mentioned what is data in our previous lessons. We know that data is units of information, and that can be collected on any topic, and this can be used for different purposes, might have different meanings, and that information is often used for scientific research in finance, in business, as well as in management and retail. And we know that in school, we've used information in science and in maths to be able to conduct investigations. The fact that you get a report at the end of the year that gives you an average is, again, data that has been generated over the year. And so the headmaster and your subject heads look at that information and they process that to create averages. Again, that is processing of data. So essentially, those are scientific skills that are being used to present data. So it's very important that data is presented in graphs. However, it's fundamentally important that we understand how to interpret a graph. So we're going to look at how we take information from a graph and interpret that better. So understanding the context of graphs is very important. Let's look at what graphs are. Graphs and charts are visual representations of data in the form of points, lines, bars, and a pie chart, as we've discussed. Using graphs or charts can display the values you measure in an experiment, in sales data, or how to use electrical changes over time. So that is information that is presented in a visual representation. To interpret that data, you need to do the following. When looking at a graph, it's important for us to read the title. What does the title give you? It gives you information about the description of what is happening or what has been recorded. So the heading often tells you or describes information about what has been collected. Refer to the text. Above the graph, there's a description around the experiment or around what has been collected. So that's important information. Check the axes. The axes are labeled to give you information. So this tells you the trend. It describes to you what is being collected. Look at the key. The key is fundamental to understanding what is being depicted in the graph. So key tells you, or in some textbooks they refer to it as the legend. The legend is important in giving you information about what is being plotted. Read the labels, guys. So you'll often find labels graph A, graph B. Check the scale. What is the scale? The scale is a proportion representation of the values that have been plotted. Look at the unit of measurement. Is it in minutes? Is it in hours? And that often helps you to understand the proportion of what that scale is. Then study the graph and try to understand what it shows. So guys, looking at a graph, it's important for us to be able to analyze that information. But before you analyze the information, use this checklist. Read the titles, evaluate the scale, look at the labels on the X and Y axes, look at the key, try and read the preamble to what has been collected, and then you get into interpreting the graph. So guys, we've gone through the first session, we've looked at the interpretation of data, we're going to try and apply this in much detail with some graphs. So you guys have done well, you deserve a break, let's rehydrate, and I'll see you back at the end of the break. Welcome back, life science learners. Remember, we're continuing with skills today, and in our lesson today we've been discussing how to interpret graphs and how to draw conclusions from those values. So let's get straight into it. Let's see how we continue interpreting graphs and use that information now to draw conclusions. So it's very important to remember, read values. You may be given values on one variable, and you may be asked to find the value of a corresponding variable. Let's go back to our graph, and we've got the independent variable on the x-axis. We've got the dependent variable on the y-axis. As I've mentioned in previous episodes, the best way to remember where the independent variable goes is look at the I. And as I mentioned, the I sits with the capital I here, and the D sits in there. So if you're ever confused, that's a hint for you. So independent here, the dependent on the y-axis. So you may be given values on one of the variables, and you'll be asked to find the corresponding value, and we refer to that as extrapolation. If you are given the independent variable, so if we go back to a graph, which I'll show you in a bit, you must first locate the value on the x-axis. You've got to then move vertically towards the graph, and then where the intercept on the graph, you move horizontally to the y-axis and read the value. So I'm going to try and illustrate that in a slide. So the question is, determine, the enzyme activity at 40 degrees Celsius. So we've got to determine the enzyme activity at 40 degrees Celsius. So the question is, what is the enzyme activity at that specific temperature? So before we get into that question, let's try and understand what is being represented in this graph. We know that on the x-axis, let's read that, we've got temperature, and it's given in the unit degrees Celsius. That's important for us to do. We also need to read the y-axis, and that's the enzyme activity, which is showing you a direction of increasing activity from the bottom as the scale increases. The heading of the graph is important because it describes to us what is being shown. So it's the relationship of enzyme activity versus temperature. Now that we've seen that, we can see that there's a trend that's shown on the graph. Let's try and understand how we extrapolate, or how do we find out if the independent variable is given. How do we determine what the dependent variable is? And in this case, I've used the example of 40 degrees Celsius. So you've got to identify the variable that has been given to you on the x-axis. So in this case, it's 40 degrees Celsius. You've got to use your ruler and draw a line vertically till it intercepts the graph. And in this case, it intercepts the graph at this specific point. Remember, you've got to have a ruler, and that's important. And then you use the ruler and you run a horizontal line towards the y-axis. And the point at which it intercepts the y-axis is the variable that you need to measure on the y-axis. So in this case, if we had a scale that represents that, we would have to measure that and read that off as a value. So this we call referring to the graph and using the scale. So go back to what we were looking at. So locate the value on the x-axis, which we've done. Move vertically towards the graph, which we've done using a ruler. Where it intercepts the graph, move the line horizontally to the y-axis and read the value. If we go back to what we've just done, that's exactly what we've done. So use a ruler and do exactly what I've done. So find the value, work up to where it intercepts, draw a horizontal line, and there, voila, you've got the answer. In this case, you've got to state the answer with the specific unit. And often learners tend to forget the unit, and they give the answer, and there's no unit, and because the unit is absent, they often tend to lose a mark, or even two. If the examiner or your teachers are difficult, you're going to end up losing a mark, because the correct scientific methodology requires that you have the answer and the unit. So that's one way of interpreting and using graphs to collect more information from that graph. If you are given the dependent variable, you must do exactly the opposite. It is not necessary to draw lines unless you are told to do so. So if we go back to that slide, so sometimes you'd be asked to determine at what temperature would the enzyme activity be, say at this point. I'm not too sure what the variable be. Say if this was 50 units. Okay, I'm using some arbitrary units. Determine the temperature at which the enzyme activity would be 50 units. So you've got to do the exact, use a ruler, join the join, see where the first point intercepts, draw a vertical line down, record that value, and that would be, I'm going to use that as 28 degrees Celsius. And you would notice that in this case you've got two lines, so it occurs twice, and so I'm going to say it occurs at 28 degrees as well as at 50, say I think it's proportionately it's around 57 degrees Celsius. So we've got 57 degrees Celsius at which it occurs. And so this is what we refer to as using information from the graph to extrapolate more data. Okay, cool. So let's move back to the next slide. Guys, if you are asked to find a value for the data point outside the range of the data, then you will need to extrapolate the curve. And I'll illustrate that in a bit. What does extrapolate mean? It means to continue the existing trend of the graph from the last data point until you intercept the required data value. Let's try and understand how that is done. So here we've got a graph. Again, we're looking at extrapolation that reads the effect of catalase on hydrogen peroxide. So we're looking at the effect of an enzyme, which is catalase, on a substance called hydrogen peroxide, and that is measured over a period of time in seconds, and the dependent variable is the oxygen release. So the amount of oxygen has been recorded, and that is an illustration of the rate of the reaction, and we're looking at what hydrogen peroxide catalase does on hydrogen peroxide. It's important to also note the key. So the key tells us that here we have liver, and here we've got the reaction for potato. So both of these substances have the enzyme called catalase that reacts with hydrogen peroxide, and they produce oxygen. And so it's a comparison between the enzyme in liver and potato, and we can clearly see that liver has more catalase. So if you were asked to find out, what would be the oxygen released at, say, 30 minutes. Now, if you look at your graph is currently plotted to a value of 25 minutes. The question is, can you determine what would be the amount of oxygen released at 30 minutes? Now, remember that your graph or data set currently stops at 25. You've got to now try and figure out what would be that reading at 30 minutes. And that process of being able to extend the data is called extrapolation. And we're going to use that to infer, without having to do the experiment, what the possible oxygen released, quantity of oxygen released would be. So that would require that you figure out the scale. And so in this case, that's the value of the scale. You will use your ruler and you'll extend the line. You would measure the proportionate scale and you would plot that point. You would then extend this point vertically upwards, and you will continue with the trend of this graph. And the best way is to look at the trend of that graph and to continue the trend of the graph until it intercepts this line. So as you would see that the trend seems to be stabilizing, so I will then use this value and I will extrapolate that back to the y-axis and determine the oxygen release. So that is how we would do that. So let's go back to that slide and see what we've just done. So you would need to extend the line. To extrapolate, you would need to, where's that? Let me go back to this. So from the graph, you would need to extend the line so that you can get the point set and find the intercept, and then you would get the required data value that you need. And that's essentially the process of extrapolation of data. Okay, so it's also important for us to be able to look at line graphs and terminology that are important. So we're looking at what are the terms that we use when interpreting graph. So there are some terms that we often have, and the example would be, as I mentioned earlier on, correlationship, directly proportionate, inversely proportionate. So these are terms that we often use when we interpret graphs. So the questions that you've got to look at: is the line a best fit line or not? And essentially we've got to understand what the term best fit means, and is it an ideal line showing the real situation? Namely, what should the data look like? So often you find that after conducting an investigation, you get, for the enzyme activity, you see a set of points that do not show a clear trend. So in science, we tend to use what we call the best fit, and that is an illustration of where most of the points tend to fall within the trend. So you would have noticed that I've ignored that point, I've ignored those, but I've tried to draw in a line that allows most of the points to fit in. And we refer to that as the best fit. However, in life sciences, we often encourage you to join all the points. And our graphs are generally a bit more simpler, where the points that have been collected can support a general line which shows a trend. If the x-axis is time, this is very important, it is useful to remember that the slope of the graph is a measure of the rate. So when you have time on the x-axis, remember that time is a state of progression. It would mean that it's an expression of the rate of the dependent variable. So you're going to see that as time progresses, there is a change in the rate of the reaction. So the steeper the graph, the faster the rate of change. So as you would see, the rate tends to stabilize here. However, if we had a graph that has a steep slope, we would say that there's an increase in the slope, which would mean that the rate is much steeper and it's occurring at a much faster pace. Okay. If we go back to the next slide, I just want to make sure pen, right, good. So in this slide, the shape of the graph indicates the relationship between the variables. Remember that straight lines represent linear relationships. So as I indicated that if you have a graph with a straight line, it shows you a linear relationship. However, graphs that slope down from the left to the right, so if we had a graph that sloped down from the left to the right, as in this case, it would give you a negative relationship, which essentially means that one variable gets bigger and the other gets smaller. Okay? Graphs that slope from the left to the right represents the proportionate relationship. As one variable increases, so does the other. So essentially, if we had a graph that has that effect, you would see that as this variable, the dependent variable increases, the independent variable increases, you find that the dependent variable also increases. So we refer to them as either a negative slope or a positive slope. And here in this, I've indicated a series of different graphs that show you the enzyme activity over a different period of time. And remember that rate is illustrated. So here you can see an increasing relationship, because as time progresses, the rate of the enzyme activity increases. This graph shows you a negative slope. So over a period of time, the rate of the reaction has decreased. Here we're seeing a graph where there is some increase for a bit, and then it gets to a point in time where the rate of the reaction becomes optimal, or it stabilizes, or it becomes constant. Here we're seeing the rate of the reaction increasing, and then we're seeing a rapid decrease in the rate of the reaction. So being able to interpret the slope of the graph talks to the relationship between the variables. So we use the trend, we use the slope to understand the relationship between the two variables. And that's fundamental in being able to infer and draw conclusions. So guys, we've looked at trends in graphs. We've looked at how we interpret that information. Let's have a short break. rehydrate, and we'll see you at the end of the break. Welcome back, learners. So we've looked at how to look at the trends in graphs. We looked at interpreting the language of a graph in terms of the slope, trying to understand what the graph gives us information around. Now let's look at how we analyze that information to draw conclusions that link to the aim of the investigation. So in this session, we're going to try and do that, and we're going to try and apply that concept to a few questions that I've put into these slides. So the analysis of results and the discussion is an important part of a scientific method. It means that you now are able to interpret and analyze the information. A discussion is important because it talks about the value of what you've collected, and that's important. It allows you to be able to reflect. It allows you to be able to link that to your hypothesis. So that's a fundamental part of scientific methodology. So the analysis of results is stating in words what the results are often saying in tables and graphs. So as I said, so often a table or graph is an illustration which is visual, but an analysis is using words to state what you've seen as a trend. Discuss if there are any relationships between your independent and dependent variables. As I mentioned early on, let's go back to that slide. So here we're seeing relationships. Discuss those relationships. Here we're seeing a relationship where there's an increase, there's a period in which it becomes stationary or remains constant, and there's a period after which there's a decrease. So that is looking at the trend in the graph and seeing trends and being able to respond to those trends. And that's fundamental to analyzing and discussing results. It is important to look for patterns and trends in your graphs or your tables and describe these clearly in words. So if we go back to the way we did this, it's important that we use values. And in this graph, we're saying, well, at this particular time, the rate of the reaction was the highest. Thereafter, it decreased for the next duration. And so it's important to use the information and create a visual description that now translates into words. Right. So how do we evaluate results, guys? This is where you answer the question, what do results mean? And when you evaluate your results, you need to be careful to consider the results the following. Were there any unusual results? So were there anomalies? Did your experiment actually give you results that you think can be interpreted? If so, these should be discussed, and possible reasons for those unusual results be explained. You need to also discuss and ensure that the validity and reliability of your investigation has been looked at. So if we go back to looking at our results, we must be able to evaluate them so that we create a bigger picture of exactly what was done. Let's review validity and reliability. So what is validity? Remember, we spoke about a fair test, and a fair test means that you have ensured that you've manipulated the independent variable, that you've kept your control variables controlled, and that you've been able to measure the dependent variable accurately. So, reliability. If the experiment were to be repeated, would the results obtained be similar? And that's, again, a measure of reliability. We've discussed what reliable means. If you think about a friend can be reliable because you know that you can trust that if you ask them to do something, that they would deliver on that. And in science, if you were to conduct this experiment again and it produced the same results, we would say that these results are now reliable. And that's reliability. The best way to ensure reliability is to repeat the experiment several times and to obtain an average. Also look for creating a range in the independent variable where applicable. For example, when you are looking at the effect of temperature on the rate of a reaction, use a range of temperatures that are consistent rather than an consistent, I'll give you an example, an inconsistent range of temperatures. So when you're doing an experiment and if you have to measure the rate of a reaction at 10 degrees, at 30 degrees, and then at 50 degrees, you often miss out information that might be important to understanding the trend between 20, 25, 35, and 40. So create a range that is more consistent so that you might be able to see the pattern or the continuity in the trend, as opposed to having a range that is not consistent. So increase the range, repeat the experiment, look for averages that are more consistent. And that talks to the reliability of your results, it talks to the validity, as well as it answers the accuracy in the way you've conducted your experiment. So let's look at the conclusion. What does that mean? It means you now need to link the results to the aim and the hypothesis. So when you write the aim of the experiment, it's often a statement of intent. When you collect the information, you want to know if that information answers the question that you've actually stated as an aim. So we often mean that collecting information means that you've got results. You do not always have to get results that support your aim. Results cannot be predicted in the sense that it will always give you the positive test. Remember that results might also give you a negative test. It's left to you to interpret those results, explain them, analyze them, and then link that to the conclusion and the aim. So in short, a paragraph, write down what was observed and whether it supported or rejected the hypothesis by restating the variables that were tested. If your original hypothesis does not match up with the final results, it means that your experiment did not change the hypothesis. Okay? So often we conduct an experiment where we find that the results do not support the hypothesis. As we mentioned at the start, you would need to go back and review your hypothesis, retest, conduct the investigation again, and see if those results are consistent. And this time around, evaluate the results and see if they now answer your reviewed hypothesis. So that's in terms of closing the circle of scientific methodology. So analyze your results, link that to your conclusion, look at the conclusion whether it supports the aim and answers the aim, and try and identify whether that hypothesis that you stated now has been proven correct or not. Cool. Let's look at the application of this in the context of some graphs. So the first question, a scientist was investigating the effect of various factors on enzyme activity. The graph below on the next slide drawn illustrates the effect of temperature on the activity of the enzyme bromelain on a gelatin solution. So guys, if you've used pineapples in the if you've eaten them or used them in an experiment before, they contain an enzyme called bromelain, and bromelain is a protein digesting enzyme, so it can break down proteins. And so we've used this enzyme in an experiment in our labs to look at the effect of bromelain on the enzymes present in gelatin. So when you've prepared jelly before, you know that jelly sets in a little while because it has the ability for the proteins to coagulate and form and become more solid and more firm. So bromelain in pineapples actually will cause the enzyme, is an enzyme that will cause the proteins to break down. So this investigation was based on an investigation to look at the effect of the enzyme bromelain on the proteins present in gelatin. Okay, so we've collected that information, and clearly here you can see that we've illustrated the effect of temperature on the enzyme activity. Guys, it's important that, as I said, see if there's a heading, and often the heading would have been, in this case, to look at the effect of temperature on the activity of bromelain enzyme. So we're looking at bromelain as the enzyme, and we've identified, well, that's the description. Look at the x-axis and determine what is being described, and that's given to you in temperature in degrees Celsius, and again it's a measure of enzyme activity on the y-axis, and in this time it's given to us in units, and these units are in a scale of units per ml, and we see that it's gone on a scale from 0 all the way to 160 units per ml. Cool. So in this experiment, the information was collected over a period of time, and we see the general trend. And for me, it's important that I've looked at the labelings, I've looked at the scale of the graph, I've also now need to evaluate what is the general trend. So I'm seeing an increase in the enzyme activity, and then I'm seeing a decrease in the enzyme activity. So at some point, the enzyme activity has reached its maximum, and then it continues to decrease beyond this specific temperature. So that's how I would interpret the information. So notice that I've looked at the graph, I've analyzed the x-axis, I've looked at the scale, I've looked at the y-axis, I've looked at the dependent variable, the unit. I've tried to understand the general trend, and now I attempt to look at the questions that are based on this. This helps me to get a better understanding of the context of the graph, and this will make it easier for you to now to interpret the information and relate that to the questions that have been asked. So the first question is, state the aim of the above investigation. And so I'll go back to the previous slide, and the aim of the investigation was to determine the effect of various factors on enzyme activity. So if we remember that, we know that the graph illustrates the effect of temperature on the enzyme bromelain. So when we go to that graph, essentially the aim is to show the effect of temperature on the rate of the enzyme bromelain, on the rate of the reaction of the enzyme bromelain. So that's the aim. Let's move on to the next question. Identify the following variables. So the independent variable, cool. So the independent variable, remember, as I mentioned, the independent variable is on the x-axis, and in this case, if we identify what's on the x-axis, it's temperature. So we're looking at the effect of temperature on the enzyme activity of bromelain. So we've identified that the temperature is the independent variable. The next question wants you to identify the dependent variable. Again, as I mentioned, remember that the dependent variable falls on the y-axis. So let's look at what was measured in this experiment that was recorded so that we could draw a conclusion. And if we go onto the y-axis, we see that it was the enzyme activity that was recorded, and that was recorded in units per ml. So we're seeing that the dependent variable is the enzyme activity, and the hint to that would be look for the y-axis, which often is the description of where the dependent variable is plotted. The next question, 1.3. Using the graph, so we've got to use the graph, identify the optimum temperature for the enzyme activity. So the optimum enzyme activity, what was the temperature at which the enzyme activity was the greatest? So if we look at the point in this graph, we see that as the temperature increases, it reaches to a point in which that was the highest rate of enzyme activity. So we identified the point. We now need to identify at what temperature this has occurred. So using your ruler, you now need to draw a vertical line that intercepts the x-axis, and you would need to proportionately scale the value at which that line intercepts the x-axis. And for me, if I look at 55, would be approximately there. So using your rulers, you would see that you could measure that, and that's probably be around 56 degrees Celsius. So remember that you've got to give the value, so it's 56, and in this case the unit, and that would be the correct answer because you've now identified the temperature by a method called extrapolation. Remember that it's often useful to indicate the line, and that line indicates the system or the method in which you got your answer or you established your answer. So it does help for the marker to see the manner in which you've reached or concluded your answer. The next question, 1.4. Using the information from the graph, describe the effect of temperature on the enzyme activity. more importantly, is the mark allocation for this. So what does this mean? We've got to now use the information from the graph to describe the effective temperature. As I mentioned, the graph has a lot of information. When I look at this graph, I see 3 possible areas that I need to comment on. That's the first phase. I also know that there's a specific point at which there's an optimal change in the activity. And then I see the second or the third phase of change, and that's phase C. Remember that, guys, when you are reporting on trends in a graph, it is important that you use the information from the graph and values to explain the trend. Often learners would say, well, there's an increase and there's a decrease, but that's just a kind of a superficial description. It's important that in scientific methods or explanations that you refer to data. The question says using information. So how do you support your descriptions of that trend? By values, by data. So it's important that you describe the trend over a particular time and you use values to support that. So I would say, well, the rate of the reaction increased from 30 degrees to around 55 degrees, from 40 units to a high of 140 units. It reached the optimal temperature at enzyme activity at this particular temperature, and then it decreased further from that till 70 degrees or 75 degrees Celsius. So I've used values, I've used the trend, and I've explained the conclusion to what the aim of this experiment was. So guys, we've rushed through this. We've looked at how to get through this. However, in a test or an exam, remember that analyze, read, try and interpret the information, use data to support your conclusions, and link that back to the aim. Guys, it's been a wonderful session. I've enjoyed the interaction with you guys. I hope that you guys apply these in the context of a scientific investigation where you need to draw conclusions and analyze information. From me to you, bye, take care, keep well.